In question 1, we'll first find f of 3. So off of the graph, that's the y value at 3. So here's 3. The y value is 1. So this exists, and I'll say is equal to 1. Okay, next we're looking at a limit. The limit as we approach -2, but only from the left side. Does this limit exist? And the answer is no, it does not exist. If you want to be specific, it looks like there's a vertical asymptote here, and the graph is going down to -infinity. So I'll say that, well, it's -infinity, but also it does not exist. And the reason for this is because there's a vertical asymptote at -2. Now, what about the limit as we approach -2, but not from the left, but from the right? So here we're looking at this part of the graph, and I don't care about the point itself, but it's definitely going up towards the y value of 4. So this limit does exist and is equal to 4. Now, what about the limit as we approach 2 altogether? Well, since it doesn't even exist on one side, it's definitely not the same on the left and the right side, so I'll say this limit does not exist, and that's because the limit from the left does not equal the limit from the right. Okay, now what about as we approach 1 from the left? So for this one here, the function isn't defined at this one open circle, but the graph is definitely going down towards -2, so the limit does exist and is equal to -2. And as we approach from the right, it looks like the y values are getting closer to 1. And again, altogether, as we approach 1, the limit does not exist. And that's because the left-hand limit is not equal to the right-hand limit. So the limit from the left does not equal the limit from the right. Okay, one more here. What about the limit as we approach 3? Now, it has to be that the limit from the left and the right are equal, and actually they both are. We're approaching 5 from the left and also 5 from the right. It doesn't matter that the point's defined down here. This means the value f of 3 itself, but the limit certainly exists and is equal to 5. It's the same on both sides. In question 2, we're given a function g. It's a piecewise function defined around -1 and 2. And I want to find the values of x where g is discontinuous, and then analyze those to see if, well, maybe it's continuous from either the left or the right. And once we find either the discontinuity or discontinuities, are they removable, infinite, or jump? Maybe just to think about these 3 terms for a second. So when we say removable, here's one way a function could not be continuous. If there is a hole in the graph and you remove the point and put it somewhere else. So here's one way that a function would not be continuous, a removable discontinuity. Infinite just refers to if you have some type of asymptote, like a vertical asymptote. Maybe it's going up on one side and down on the other. So this is an infinite discontinuity. And then lastly, this jump discontinuity means you have a split in the graph. The graph actually jumps either up or down. So not just a hole, but an actual break in the equation itself. Here are 3 different types of discontinuities. Now, the function g is broken into 3 separate pieces, and each piece in and of itself is continuous. So really, there's only 2 numbers that we have to check for discontinuities, either at -1 or at +2 where the break happens. So let's first examine what happens at x is equal to -1. Is the graph discontinuous here? So what we can do is look at the limit as we approach -1 from the left of the function g. That is equal to the limit as x approaches -1 from the left of, and here we're using this part of the function, which is 2 minus x squared. And so to compute the limit, you would put -1 in place of x. You get 2 minus -1 squared is 2 minus 1, or 1. So here's the limit from the left. If you look at the limit from the right, the limit as we approach -1 from the right of the function g of x. Okay, that means we're now working here. We're approaching -1 from the right side because x is greater than -1. So we'll use this as our equation. So this is the limit as x approaches negative 1 from the right of now 2 minus x. This time when we put negative 1 in place of x, we get 2 minus a minus, or 2 plus 1, which is 3. So what does this mean about our function? On one side it's approaching 1, and then it jumps, and on the other side it's approaching 3. So at x equals negative 1, it is discontinuous. And in fact, it is a jump discontinuity. And the reason is, on one side we're approaching 1, and then it jumps up to approach 3 on the other side. Now, expanding on this further, even though it's not continuous at negative 1, it might be continuous from the left or the right, or actually maybe neither side. So let's figure that out too. We need to know what g of negative 1 is equal to. Well, I have to use the part with the equal sign with the negative 1, so we're talking about this middle part here. And 2 minus a negative 1 is 3. So if we're continuous from the left, it would have to be that this thing is equal to g of negative 1, which it isn't. So this is not equal to g of negative 1, because g of negative 1 is 3. So this is definitely not continuous from the left-hand side. But is it continuous from the right-hand side? And the answer is yes, because g of negative 1 actually is 3. So even though it's not continuous, it is continuous from the right. So I'll just note that up here. Continuous from the right. Okay, so moving on, the last thing to check is, well, what about at positive 2? Is this function continuous there? So let's check. At x is equal to 2, if we look at the limit from the left of g of x, if we're approaching 2 from the left, we're using this portion of the function, so 2 minus x. So this is the limit as x approaches 2 from the left of 2 minus x. And if you put 2 in place of x, you get 2 minus 2, which is 0. So that's the limit from the left. The limit from the right, as we approach 2 of g of x, okay, that's the limit as x approaches 2 from the right of, so this is x minus 2 squared. Now, if you put 2 in place of this, you get 2 minus 2 is 0, and if you square that, you get 0. So here, the limit from the left is equal to the limit from the right. If the value of the function is actually at that spot, at 2, we can say this function is continuous. So let's check that. What is g of 2 equal to? Well, we have to use this portion of the equation, and if you put 2 in place of this x, you get 2 minus 2, which is 0. So what we have is the limit from the left and the limit from the right are equal, and they're both 0. And they also equal the value of the function at this point. So we just showed that the limit as x approaches 2 of g of x is actually equal to g of 2. So this is continuous at x is equal to 2. So we don't really have to consider this from the left or right in either part. There's actually only one discontinuity. It was at negative 1. It was a jump discontinuity that was continuous from the right but not the left. Let's compute the following limits or explain why they don't exist. Starting with this one here. You can think of putting 1 into all the x's, and when you do, you get 1 minus 1, which is 0, and then the denominator of 1 minus 1, which is 0 as well. This is a 0 over 0. That doesn't mean it doesn't exist. It means we probably can simplify this a little bit. So let's try to figure that out. So we should be able to write this as the limit as x approaches 1 of, well, I know how to factor the denominator. That's x minus 1 times x plus 1. And the reason the denominator is 0 is because there's a factor of x minus 1 in it. If you put 1 in place of x, you get 0. So it should be that you can factor out x minus 1 from the numerator too. It'll be x minus 1 times, something else. And if we can figure out that thing, it'll help us figure out this limit. One way to figure this is, there is a formula for the difference of 2 cubes, and there is a way to factor it. We actually can also just use long division. You can say, well, if I try to divide x minus 1 into x cubed minus 1, what comes out? And with long division, that's going to be x cubed 0x squared plus 0x minus 1. We try to cancel the x cubed, and I'd multiply x by x squared to get x cubed. So I'll say, okay, we got x squared. Multiplying x squared to x minus 1 gives us x cubed minus x squared. When we subtract this away, we change the signs, and we end up with x squared, and I'll bring down the 0x. We now want to cancel x squared by multiplying this by something, and that thing is going to be x. And when I do, I get x squared minus x. If I subtract this, I change the sign on both of those things, and we have x minus 1. To complete this division, if I multiply x minus 1 by 1, I get x minus 1. And if I subtract that by changing the signs, I have my remainder of 0. And what this means is if you divide x minus 1 into x cubed minus 1, you get x squared plus x plus 1 that comes out, which is this thing. It's at this point where we can say, okay, I'll cancel those factors. This is the limit as x approaches 1 of x squared plus x plus 1 over x plus 1. And if you put 1 into all the x's, which you're allowed to do, you get 3 over 2, and that's the final answer. So for factoring a cubic, there is a formula for it, but if you don't know it, you can always figure it out by doing long division. To compute this limit, we're going to divide the top and bottom by the highest degree x, which the bottom has x to the first, and technically in the numerator, this is a square root of x squared, so it's also an x to the first. So the idea for this problem is we're going to take the limit as x approaches positive infinity. We'll take the numerator and divide it by x, and then we're going to do the same thing with the denominator. This gives us 1 over x minus 2x over x. So we divide the top and bottom by x. That should have been an x. Okay, we can simplify a little bit. I think I'll do that next. This is the limit as x approaches infinity of, and in my denominator, well, I can't do anything with the 1 over x, but 2x over x is just 2. I'd like to move this x somehow into the square root to break this up into a couple of pieces. And the way you can do that is by using the following identity. The square root of x squared is equal to the absolute value of x. However, since we're approaching positive infinity, there's really two choices, right? You could say that the square root of x is either the positive solution or the negative solution of x. X approaching positive infinity means we're going to use the identity the square root of x squared is equal to x, the positive one. Had this limit been going to negative infinity, I would have used negative x instead, and that's important with the answer that you'll get. All that being said, the numerator is now the square root of 16x squared plus 1, all divided by the square root of x squared, because x and the square root of x squared, in this case, are equivalent. But if you have a square root with fractions, you can re-express this as the limit as x goes to infinity of the square root of the entire fraction. So 16x squared plus 1 over x squared. This is the trick for getting the x squared into the square root, because now you can divide this into the two fractions. That is, you get the limit as x approaches infinity of, I have 1 over x minus 2, again in my denominator, and in the numerator I have 16x squared over x squared. I'm going to write that as just 16, plus 1 over x squared. So what happened here is this x squared canceled, leaving us with just 16, and then 1 over x squared leaves me with 1 over x squared. Let me draw that a little better. That's supposed to be a 2. Okay, so what next? We're very close. We're going to take the limit of the denominator. This goes to 0, and that's going to be negative 2. Here, the square root of x is a continuous function, so you can move the limit inside of it and attach it to the 16 and also the x squared. I'm going to do that as my next step. So coming up here. This is really the square root of the limit as x approaches infinity of 16 plus the limit as x approaches infinity of 1 over x squared. And this is divided by the limit as x approaches infinity of 1 over x minus the limit as x approaches infinity of 2. So I broke the limit up between the numerator and the denominator. The root function is continuous, so the limit can go inside of it, and I put it next to both pieces, and I decided to put the limit next to both pieces of the denominator as well. With all that being said, we can now evaluate each piece. This will be the square root of just 16 plus 0 divided by 0 minus 2. So that's the square root of 16 plus 0 divided by, in the denominator, 0 minus 2. Well, the square root of 16 is 4. Divided by negative 2 gives me an answer of negative 2. This is the answer for this limit. So here I have a limit with a square root in the numerator. And again, can I maybe just put 0 in place of x? And the answer is no, because you'll get 0 over 0. But we saw a nice trick where if you want to cancel these square roots, what you can do is multiply the numerator and the denominator by the conjugate. So I'm going to do that as my first step. I'm going to multiply the top by the square root of 4 plus x plus 2 instead of minus 2. I'll do the same thing in the denominator as to not change the value of the limit. Okay, when we do this and we distribute out the numerator, we get the limit as x goes to 0 of, I'll write the denominator first. I'll put x times the square root of 4 plus x plus 2. I'm not going to multiply in the x because at some point I want to cancel this thing, and leaving it by itself will be helpful. In the numerator, when I do the square root of 4 plus x times the square root of 4 plus x, that's the same thing as squaring the square root of 4 plus x. And so that's what you get, 4 plus x. You'll get two middle terms. One's positive and one's negative. You'll have positive 2 times root 4 plus x, and then negative 2 times root 4 plus x. They cancel. I'm not going to write them. Instead, I'll just do negative 2 times 2, which is negative 4. So this trick will cancel the middle terms. And that's a great thing because this is the limit as x goes to 0 of, well, the 4's cancel and I have x. In the denominator, I have x times the square root of 4 plus x plus 2. We are now allowed to cancel the x's, so those are gone. There's really just a 1 in the numerator. And this is the limit as x goes to 0 of 1 over root 4 plus x, then plus 2. We are allowed to put 0 in place of x. And when we do, this is the square root of 4, which is 2. And when you add that to 2, you get 4. And therefore, the answer to this problem is 1/4. What about the limit as x approaches infinity of this fraction? Now, this isn't a rational function because we have e to the x, the exponential function. Maybe just a reminder off to the side. If you look at the exponential function e to the x, it looks something like this. It's an increasing function. And by looking at the graph, as x approaches infinity, as we head in this direction, the y values, e to the x, go to positive infinity. And the reverse happens when we go to negative infinity for x. So when x approaches negative infinity, here the y values, e to the x, are approaching 0. Using this idea, I think we can figure out this limit, and we're approaching positive infinity. The idea is to divide the numerator and the denominator by the highest x term in some sense. And in this case, that's going to be e to the x. I'm going to divide every term by e to the x. So this limit is equal to the limit as x approaches infinity of, that's 9 divided by e to the x, plus e to the x divided by e to the x. In the denominator, I have 2e to the x divided by e to the x, minus 1 divided by e to the x, this thing. We can simplify it. This is the limit as x approaches infinity of, okay, so we have 9, that was supposed to be 9, over e to the x plus 1. And then we have 2 minus 1 over e to the x. Okay, so we're getting close. I think I'll actually put the limit into each part of the fraction. So this is equal to the limit as x approaches infinity of 9 over e to the x plus the limit as x approaches infinity of 1, all divided by the limit as x approaches infinity of 2 minus the limit as x approaches infinity of 1 over e to the x. Well, the 1 and the 2 here in these limits don't matter. We can just cancel limits and put 1 and 2. And here, e to the x is going to infinity. That means a number over something going to infinity goes to 0. This is 0, and this is 0. This means if we want to figure out the answer, it's going to be 0 plus 1 divided by 2 minus 0, and that is 1/2. So what about this problem? It's the same limit, but we're going to negative infinity instead of positive infinity. And again, just to recall the graph of e to the x, here's e to the x. And as x approaches negative infinity, e to the x is going to approach 0. In this question, it's tempting to divide everything by e to the x. But actually, it's even simpler than that. Since we're approaching negative infinity, e to the x goes to 0, and this e to the x goes to 0. So those terms are just going to cancel in and of themselves, and leaving us a 9 and a negative 1 left over. So to figure out this limit, we can simply just move the limit as x approaches negative infinity into the numerator and the denominator. That is, this is the limit as x approaches negative infinity of 9, plus the limit as x approaches negative infinity of e to the x. This is all divided by the limit as x approaches negative infinity of, maybe I'll put this one as 2 e to the x. I can move that 2 outside of the limit, and then do minus the limit as x approaches negative infinity of 1. The reason for this is a constant, so the limit is just 9. Plus, by this graph and moving in this direction, the y values go to 0, so I can just call this thing 0. This is 2 times something going to 0, so it's going to be 2 times 0, and then minus 1. When you simplify this, you get 9 over negative 1, and that's just negative 9. And that's the answer for this limit. In question 4, part A, we're given a function, and we're asked for any epsilon greater than 0, can we find a delta such that if this condition holds, then the absolute value of f of x is less than epsilon? Essentially, what this question is asking us to do is figure out the limit as x approaches negative 1, because that's the number that makes this equal 0, of the function f of x. And here, if you put negative 1 in place of x, I know the answer you're going to get is equal to 0. Like, this is what it's asking us to do. I'm going to do this in 2 steps. I'm first going to actually find the delta and then prove that this statement is true. So first, I want to find delta. The way we do that is by looking at the absolute value of f of x and showing that it's less than epsilon. Now, there's no other number here, but that's because the limit is supposed to be 0. So what I'm going to do is actually write in, it should be, f of x minus 0 in absolute value, and that thing's less than epsilon. So next, I'll replace f of x with 5 plus 5x, and I really don't need the 0 anymore, so I won't write that. I'll say, we want this thing to be less than epsilon. Well, from here, I can factor out a 5, and I guess I should write that as 1 plus x. And you can break the 5 out of the absolute value and just put 5 absolute value of 1 plus x. And that's equal to 5 times the absolute value of x plus 1. The order in which you add them does not matter. We want this to be less than epsilon. If you divide both sides by 5, you get the absolute value of x plus 1 is less than epsilon over 5. And this is going to be our delta here. And that takes us to the second step, which is to actually prove this statement. Like, did we do this? So I'll let epsilon greater than 0 be given. I will choose delta equal to epsilon over 5. And I'll just note that, we wanted a delta that's greater than 0, and this delta certainly is. Okay, next we'll assume that the absolute value of x plus 1 is less than this delta. We have that the absolute value of f of x is equal to the absolute value of 5 plus 5x, which is equal to the absolute value of 5 times 1 plus x, which is equal to 5 times the absolute value of 1 plus x, which is the same thing as 5 times the absolute value of x plus 1. And now we made this assumption. We are assuming that just this part is less than delta. That means 5 times this thing must be less than 5 times delta. Of course, delta was chosen to be equal to epsilon over 5, and by virtue of choosing a 5 in the denominator, they cancel, and it leaves us with just epsilon, and that concludes the proof. For part B, given that 3x is less than f of x is less than x cubed plus 2 on this interval, can we determine this limit, the limit as x approaches 1 from the left of f of x? And here we know nothing about the formula for f of x. In this instance, we can use the Squeeze theorem. Here's the observation to make. We don't know f of x, but we can look at 3x and say, well, what happens to that as we approach 1 from the left? The limit as x approaches 1 from the left of just 3x is, well, you can put 1 in place of x and you get 3 times 1, which is 3, okay? Now you look at the other function, so the limit as x approaches 1 from the left of, and that's x cubed plus 2. And if you put 1 in place of x, you get 1 cubed, which is 1 and 2, and that gives you 3. So we just showed that, okay, this thing approaches 3, and this thing approaches 3. And this function is always trapped between these two on this interval. In this instance, the Squeeze theorem asserts that under these conditions, you know the limit as x approaches 1 from the left of f of x, it is forced to be 3 as well. So if this one goes to 3, and this one goes to 3, and this is always between those two things, then this has to go to 3 as well. In question 5, part A, I want to show that this polynomial has a real root. And by that I mean, if you plug some number in place of the function, you'll get 0 back. And we call this thing a root. I want to show one exists. We don't necessarily have to find what it is equal to. To do this, we're going to use the intermediate value theorem. So what I'm going to do is I want to find a number where this function is negative. And then I want to find a different number where this function is positive. The intermediate value theorem says that if you have a continuous function, like this polynomial, you'll get all the y values in between the negative and positive number. And since 0 is one of those, that's our way of saying there is a solution to the equation. Now we gotta be a little clever here. I want to think of an x value that if I put it into this equation, I get some negative number back. The most obvious choice for me is using the number 0. So if you use x is equal to 0, p of this number is equal to -1. So p of 0 is negative. Actually, I'll just leave it as this. Okay, the next thing I'd like to do is figure out, is there some x value when I put it in place of here, I get a positive number. I don't think 1 is going to work, but maybe 2. Let's see. So I'll try 2. If I put 2 into this function, I get 16 minus 2 times 4, which is 8, minus 2 minus 1. So p of 2 is equal to 16 minus 8 is 8, minus 2 is 6, and minus 1 is 5. So this worked out pretty nice. So here's what we know. On the interval from x equals 0 to x is equal to 2, I know that p of 0 is negative. It's less than p of 5, which is positive, and therefore the number 0 is the y value between them. Since p of x is continuous, by the intermediate value theorem, there is an x value such that p of x naught is equal to 0. And that proves the existence of this root, even though we don't know what it is. Now, same idea for part B. I want to show that this function has a root. That is, you can find a number, some number x naught, where when you put it into this function, you get 0 back. So this is a root. And I want to do this again by using the intermediate value theorem. One of the assumptions that we need is that this function is continuous. Well, x and e to the x are both continuous. They're continuous on the entire real line. So you could say even from negative infinity to positive infinity. And so their sum is continuous on the entire real line too. So we're working with a continuous function. That's a good thing. The next thing that we need is, I want to find some value of x where this thing is negative, and then another one where it's positive. And the second we have that, we'll know the existence of this root by this theorem. So a place where this is negative, I think I'm going to let x equal -2. If I put that into the function, f of -2 is equal to -2 plus e to the -2. Now, what does that simplify to? Well, that's -2 plus 1 over e squared. Now, if I'm not using a calculator, e is roughly 2.7. And so if you square e, let's see, well, if you square 2, you get 4, and if you square 3, you get 9. So yeah, maybe it's roughly an eighth or something like that. I'm not really sure exactly what it's equal to. But what I do know, this number, when added to -2, is not big enough to make it positive. So even though I don't know what the number is, I do know that at -2, it is a negative number. Now I need to find a place where the function is positive. I think that'll be a lot easier. Maybe even, I think the number 1 should be good enough. F of 1 is 1 plus e to the first, and e is about 2.7. If you add 1 to it, you certainly get a positive number. So here's what we have. By the intermediate value theorem, I know that f is continuous on the interval from -2 to 1. I'm choosing -2 and 1 because that's a spot where I know that's negative and then it's positive. So f of -2 is less than 0 is less than f of 1. So therefore, by the intermediate value theorem, there exists an x naught in the interval from -2 to 1 that is a root. And that is enough to justify the existence of the root here. Let's find all horizontal and vertical asymptotes of this function. To start with, if we're looking for the horizontal asymptotes, that is the limit as x approaches infinity of the function. If this thing levels off to a number, either if you're going to positive or negative infinity, that number is a horizontal asymptote. So this is the limit as x approaches either positive or negative infinity of 2x plus 1 over x minus 3. Our trick for dealing with this is to divide the top and bottom by the highest powered x term from the denominator, which is x. So that's 2x divided by x plus 1 divided by x. Then we have x divided by x minus 3 divided by x. So this is the limit as x approaches either plus or minus infinity of, so that's 2 plus 1 over x divided by 1 minus 3 over x. The 2 and the 1 don't change, but 1 over x and 3 over x go to 0. Therefore, we have 2. So y is equal to 2 is our horizontal asymptote. Now, what about a vertical asymptote in this equation? So that's going to be wherever your denominator is 0, but your numerator is not. So I can tell that there's exactly one number where this happens. That is x is equal to positive 3. And again, this makes the denominator 0 and the numerator non-zero. If we're using limits to explain our answer, what we could do is look at the limit from either the left or the right as we approach the number 3. So in this function, what happens as you approach 3 from the left of f of x? So that's the limit as x approaches 3 from the left of 2x plus 1 over x minus 3. Now, as you approach 3 from the left, your numerator is going to give you positive numbers, and your denominator is going to give you negative numbers. And therefore, it's going to infinity, but specifically negative infinity. That's enough to say that here, at 3, there's a vertical asymptote. But just to be careful, you can look at the right side too and say, well, what happens as you approach 3 from the right of this function? And as you approach 3 from the right, you're still looking at 2x plus 1 over x minus 3. Okay, in this case, both the numerator and the denominator are approaching positive numbers, so this limit is going to positive infinity. This is enough to indicate that there's a vertical asymptote at x is equal to 3, and that is the only one that exists for this function. Let's use the limit definition of the derivative to find f prime of x for this function here. So we'll start with that in part A. So f prime of x is equal to the limit as h goes to 0 of 2 times x plus h squared plus 3 times x plus h plus 1. Then we want to subtract off the function itself. So we're subtracting off 2x squared plus 3x plus 1. And this whole thing is divided by h. So again, what I'm using here is the definition of the derivative. That is, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So be careful with this minus here. I use parentheses because we're subtracting the entire function. Our job is to now carefully simplify this thing. So if you have x plus h squared, that's x squared plus 2xh plus h squared. If I double that, that's 2x squared plus 4xh plus 2h squared. If I distribute in the 3, I get plus 3x plus 3h. And then that plus 1 tags along. I then distribute the negative, I get negative 2x squared minus 3x minus 1. And this is all over h. It should be that a bunch of stuff cancels. The 2x squareds do. What else? Oh, the 1 and negative 1. And we have a negative 3x and a positive 3x. And the good news here is that the only stuff left over has h's in the numerator, which means we can cancel it with the h in the denominator. This is 4xh plus 2h squared plus 3h all over h. If we factor out h from the numerator, we get 4x plus 2h plus 3 over h. Those h's cancel. This is the limit as h goes to 0 of, don't need a fraction here, let's get rid of that. It's of just the expression 4x plus 2h plus 3. When I put 0 in place of h, I have 4x plus 3 left over. And this thing here is the formula for my derivative. So from part A, with this function, we got this as our derivative. Let's use this information to find the equation of the tangent line at x is equal to 2. And I'm going to use the point slope formula, y minus y1 is equal to m times x minus x1, this thing. To get this equation, I need the slope of the tangent line as well as a point that is on the line. To find the x1, y1, what we can do is put the number 2 into the original function. So if you put 2 into this function, 2 squared is 4 times 2 is 8. 8 plus 1 is 9. And if we add 6 to that, that's 15. So here's our point. It is 2 for x and 15 for y. But we also need the slope m. And the slope m is equal to the derivative evaluated at 2. And here that's going to be 8 plus 3, and that's 12. Going from here, I'm just going to put all this information into the equation of the line. That's y minus 15 is equal to 12 times x minus 2. I'm going to simplify it to y equals mx plus b form, but that means y minus 15 is equal to 12x minus 24. And if I add 15 to both sides, I get y is equal to 12x minus 9. And that is it for this problem.